This video is going to be about, it's from the one review set of stations for optimization. So just going over the solutions. So whenever you're doing these problems, what you want to do first is write out your goal. So you understand where you're going with this problem and what you're going to have to be doing. Sometimes you're going to have more than two or more functions and you got to know which one you want to take the derivative of. So the first problem here, find two numbers whose sum is 540 and whose product is as large as possible. So our goal here is to maximize product. Since you're going to find the max or min of the product function, we're going to need to find p prime, or derivative of the product. So two numbers. First one's going to be x, could be whatever it wants to be, whatever you want it to be. Second number is going to be 540 minus x. Since you know whatever x is, okay, in order to find the second one, the sum minus the first number gives you the second. So for example, if you say the first number is 30, how do you get the second number? 540 minus 30. So it gives you that second number. Okay, so you can take various sets of numbers that have a product that adds up, a sum that adds up to 540, but they give you different products. So which set of numbers gives you the maximum product? So product is first number times second number, distribute. Now once you have your product function, again you substitute x in, any number in for x, that tells you what that product's going to be. So what I want to do now is find the critical points. That's where your max and min are located, your extreme values. So take the derivative, set it equal to 0. So derivative equal to 0, and I get x equals 270. Now in order to see 270, that's a max or a min, what I use for all these problems is the second derivative test. We talked about the first derivative test in which you use the sign chart. You plot your critical point 270, substitute number to the left of it, number to the right of 270, and look at the sign changes. And what you end up seeing is increased and decreasing, so it makes 270 become a max. Using the second derivative test, which I'm going to be doing for the rest of the problems, you take the second derivative and it's negative 2. Now notice how there's no x there. That means since we only have one critical point, it's going to be a max or a min. There's no choice what it's going to be. So this critical point, since the second derivative is negative, that means the function is concave down. And concave down means that our one and only critical point is going to end up being a maximum. So if you just draw a little picture of the concave down, you see your critical point is going to be a max. And again, there's no x here because there's no choices if it's a max or min. It is what it is because there's only one of them. If there were two, then one's a max, one's a min. Substitute it in to find out what it is. Okay, the second type of problem. Okay, area and perimeter. So, girl wants to fence around a property. You have this much fencing. So you got to think, what are you given? Are you given the perimeter or are you given the area? So if you have this much total fencing, you're given the perimeter. So 12,000 feet of fencing. What should the dimensions be in order to yield the largest area? So what is our goal here? What are you trying to do? We're trying to find the maximum area. So if I want to find a max or min of an area, I'm going to end up doing a derivative a prime. So again, our choices are area or perimeter. That's our two functions we're working with. And so maximizing area, there better not be any p primes, just a prime. Okay, so area, if I draw my picture, is x times y. Now the problem is, so you have to do implicit differentiation. You want area to be a function of one variable. Right now it's a function of two variables, x and y. So what I need to do is eliminate one of these variables. And the way I do that on the side is, I know what the perimeter is, 2x plus 2y. I'm adding the four sides up. I know the perimeter is 12,000. So if I have 2x plus 2y equals 12,000, I can solve that for one of the variables. So in this case here, I just solved it for y. It really doesn't matter. X or y is fine. So I solved it for y. And I'm going to substitute this into the area function. So that now, instead of x times y, this is my x times y. So now my area is now a function of one variable versus two variables. Okay, now that I have this, take the derivative, because critical points are where your max and min occur, if you have any. So again, if you have a max or a min, they're either going to be at the end points or at the critical points. So find our critical points, so take the derivative, set it equal to 0, solve, and x equals 3,000 for one critical point. So now, is that 3,000 going to be a max or a min? So I'm going to use the second derivative test. So take the second derivative, which is just negative 2. And again, there's no x because I only have one critical point. That means that one point's going to be a max or a min. And because this is negative, that means our function's concave down, proving that our critical point is a maximum. It's up there. So what did we find the maximum of? We found the maximum area. We proved that this number gives us the maximum area. So now I have x. I substitute in here to find my y, which is 3,000. So now area, 3,000 times 3,000, 9 million square feet. So again, these are the dimensions that give you the maximum area with 12,000 feet of fencing. Okay, and back to something geometry, more squarish a shape is, I guess you could say, the more area it gives for the given perimeter. So those are the dimensions for 12,000 feet of fencing that yield the largest area. Okay, see, hotel here, the management wants to create the smallest room possible while still having a mandatory 5,000 or 500 square feet. So now what are they giving you? 500 square feet, that's going to be the area. Okay, so we're going to fit as many rooms as possible. What are the dimensions to help accomplish this? So if I'm trying to find the smallest room possible, my goal here is to minimize perimeter. So between area and perimeter, I'm going to need to minimize perimeter, so I'm going to be using P prime. So just like before, perimeter is 2x plus 2y, but again, perimeter is a function of two variables, and it can be a function of one variable to work with. So I need to eliminate one of them. So what I'm given is the area is 500, area is x times y, so 500 equals x times y, y is 500 over x. So I'm going to take this, substitute it in y, and again, it doesn't matter which variable you solve for. You get the same thing anyway, and just find the other one at the very end. Whichever one you found first, find the second one. So when I do my substitution, now I have perimeter as a function of one variable, just p of x. Simplify. Now I'm going to write this into a format that I can take the derivative easily. And you can do quotient rule here, but that's sometimes a pain. It's easier to just do a power rule. So p equals 2x plus 1,000 x to the negative first. So now it's find the max and mins of the perimeter function. So I'm going to take the derivative set equal to 0 because my max and mins occur at the critical points. So p prime is 2 minus 1,000 x to the negative 2. So set this equal to 0. And you end up getting two solutions. Okay, remember that from algebra. The fundamental theorem of algebra, whatever your degree at the polynomial is, that's how many solutions you have, plus or minus square root of 500. However, for the context of this problem, we'll throw out the negative because you can't have a negative length or negative dimension of a room. So positive square root of 500, 22.36. Okay, now is this point going to be a max or a min? What is it? So I'm going to use the second derivative test again. So I'm going to take the second derivative, p double prime, and you get 2 plus 2,000 over x cubed. Substitute our critical point into the second derivative, and you end up getting a positive answer. I just ran out of room to write it. You end up getting a positive answer, which means this is concave up. At that critical point, at this point, the function is concave up, which means that point you found is a minimum. And what is it that you found the minimum of? You found the minimum perimeter. So 22 minimizes your perimeter. So we fit our goal. Now 22 is one dimension. Substitute it in for x to find your y, and you get 22.36 again for the other dimension. So 22.36 by 22.36 is the smallest dimension, the smallest room, which will give you 500 square feet. Okay, number 4. Okay, Don wants to build 4 pens for his pigs in his home. He has 180 feet of chicken wire that he wants to use to create 8 pens. 2 rows of 4. What should the dimensions of each pen be in order to maximize the area of each pen? So again, our goal here is we're going to maximize area. So what function are we taking the derivative of? A prime. Okay, so now I make my drawing. I have my 8 pens. Now with this, each pen, I'm going to make my X mean a vertical piece, my Y is mean a horizontal piece. So this is X, 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 X. Okay, so I have 8 X's. 1, 2, 3, 4, 5, 6, 7. No, sorry, 10 X's. And now how many segments of Y do I have? So I'll make my Y a horizontal component. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So my perimeter is going to be 10x plus 12y. Now you might think, well, isn't it also, 2x is the length of this side, and 4y is the length of this side? The problem is, if you use that for your perimeter things, you're going to be finding the dimensions that give you the area of the entire space, where if we just use regular x and y as individual components, our final answer will be in terms of 1 pen, which is what we're trying to find, 1 pen. So if you do it as a whole, it'll give you maximum area or whatever you're trying to find of the whole thing, but I always want to do each pen individually, and you just multiply it by 8. It just makes it a little more convenient. Alright, so starting with the area function, area is x times y. So again, you have a function of 2 variables, you want to have a function of 1 variable. So I'm going to take our perimeter function, solve it for x or y. It really doesn't matter. I just solved it for x. No special reasons, just did it for whatever. Okay, so x equals 18 minus 1.2y. So again, once you have a variable solved, I'm going to take this and substitute it in for x, right here. Okay, it goes in for x. So distribute, so a is a function of y, 1 variable. So find the critical points. Where does max min occur? So take the derivative, set equal to 0, and you get the y to be 7.5. So the pink dimension is 7.5, and as that can give us a maximum or minimum. So this critical point, in terms of it's a max or min, I take the second derivative, which is negative 2.4. So our one only critical point is at a concave down, which means it's a max. And what is it you're maximizing? Maximized area. So y equals 7.5 will maximize your area. Because again, this is an indicator of what the critical point is. It tells you if it's a max or a min. So the one and only critical point is going to be a max. So now find find x. Substitute y into this equation, and you get x is 9. So our dimensions of each pen above in our diagram is 9 by 7.5. Let's see, our units are feet. So the area per pen is 67.5 square feet. Okay, volume. Okay, this is the kind of problem where you start with a sheet of paper and you cut congruent squares out of all 4 corners. Cut congruent squares out of all 4 corners so that when you chop them off, it looks like this. And then these 4 sides you can fold up to make a box. Okay, so we did that in class and it looked like this. Tape off here. Okay, I start with a sheet of paper. I cut the 4 sides off, or 4 corners, and then when I fold them, they make a box. Okay? So, my length, my width, since each of the cuts are congruent, whatever this is, equal to this, equal to this. Whatever this length was, the original, this length is now going to be that number minus 2x. Same thing with the width. Now x is the length of your cut, okay? This cut and this cut are congruent. So since this is the length of cut, when I fold my box up, so here's my cut, it's x, 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 like I drew in the picture. When I fold it up, you see that the height of the box, height is going to be x. The height of the box is x units high. So that's how I get the height to be x. And again, like I said here, if the original length of the sheet of paper was 9, and I cut off x on the left and x on the right, this piece is going to be 9 minus 2x. So here are my dimensions, 9 minus 2x by 5 minus 2x by x. Substitute, multiply, FOIL, distribute. Okay, so now my critical points, where does the maximum volume occur? So derivative equal to 0. Derivative equals 0. And for here, what I just did was you could use a calculator, the 0 function on it, which finds your roots or solutions, or what you could do by hand is quadratic formula, completing the square. Again, those are different other methods you could use to solve a quadratic that's not factorable. Okay? So my two critical points are 1.03, 3.64. Now, which one's a max, which one's min? So what I do is my second derivative test. I take the second derivative, which is 24x minus 56. I substitute 1.03 in for x, 3.64 in for x in the second derivative. One of them I got a negative answer, the other one I got a positive answer. So the negative means I'm concave down, positive means I'm concave up. So now your goal, what are you trying to find? What are you trying to find the volume? Are you trying to find maximum volume or minimum volume? So maximum volume occurs when I'm concave down, a negative second derivative. So concave down, so this number, that's my cut, that gives me maximum volume. So if you substitute both of these in, this will give you your minimum volume of 0 actually, and this will give you your maximum volume. So when I substitute 1.03 in for all three of these dimensions, I get those, and there's my volume. Okay, next one. Okay, what I'm trying to do is to have a cylinder or a jar of some sort. Okay, some sort of jar, and I want this jar to have a volume of 3 liters, and I want to find the dimensions of the jar that cost the least to create. So basically, I minimize the amount of material used to create this jar and still hold 3 liters. Okay, so my goal here is to minimize my material or minimize surface area. So I'm going to do SA prime. So formula for surface area. Surface area is 2 pi r squared plus 2 pi r h. Just like before, I have a dilemma. I have a function of 2 variables. So once again, I need to eliminate a variable in order to have a function of 1 to successfully do this problem and take the derivative. So what I'm going to do is use another formula from other information I know. I know the volume is 3 liters. So volume is pi r squared h. So now one problem is my radius and height unit-wise. Radius is in terms of either inches or centimeters, something like that. Same thing for height. Now if I have inches and centimeters, my volume can't be in liters. They don't match. So what I do is convert my volume into a unit of measure that is the same as my radius and my height. So 1 liter is 1,000 cubic centimeters. So that means 3 liters is 3,000 cubic centimeters. So now if I change my volume to cubic centimeters, my radius and height will also be in centimeters. So my units are consistent. That's why this got changed to 3,000, just because of units. So I have centimeters cubed, square centimeters, and centimeters. It all multiplies together. So, same thing as before. I have a volume formula, solve it for a variable. I can solve it for R or for H. But the problem with R is I get two solutions. So I have two equations I gotta try and mess with. So you know what, to avoid the headache, just solve for H. So divide by pi r squared. So H is 3,000 over pi r squared. So now I'm going to take this, my height, and I'm going to substitute it in for H. So I have this. So now I have a function of just R. R, R, R. Clean it up, simplify. Clean it up. Now find my critical points, that's where your max and mins are. Take the derivative and set it equal to 0. Derivative, set it equal to 0. Solve. And the rest is just algebra. And end up getting for a radius of 7.82 centimeters. Now when you use your calculator, don't forget the 4 pi. Make sure you have parentheses around it, because if you don't do that, that's going to think 6,000 divided by 4 times pi. Where you want to do 6,000 divided by the whole chunk, 4 pi. This is a common student mistake. And again, on your calculator, you could always do, instead of looking for a root key, take it to the 1/3 power. But again, make sure it's the 1/3 is in parentheses. Okay, once you have a radius, you have to prove is this max or min. Take the second derivative, substitute 7.82 in, and it's positive. Concave up means it's a minimum, and what is it that you minimize? We minimize our surface area. So substitute this in to get your height and surface area. Okay, last problem, business problem. Profit. You want to goal here is to maximize your profit. Profit is revenue minus cost. R function minus C function. Once you have a profit, find a critical point by setting derivative equal to 0. Critical points, which one of these production levels maximizes profit? Use the second derivative. And there it is. And it's in thousands of units, so I make thousands of units. And then this problem here just utilized a formula.